Hi, I'm a PhD candidate at the University of Queensland, supervised by Redshaw. And today I'll be talking about metacognition in probability and possibility judgments. If I walk into a conference and glimpse someone in passing, based on the group that they are with and the knowledge that I have of where I am in the world, I might integrate all of that information and weight the evidence to form an idea. Specifically, I might think that I recognize them. However, just as I'm aware that I simulated that possibility, I can also simulate alternative possibilities. For example, I might be incredibly jet-lagged and hallucinating. This also serves as a disclaimer to the rest of the talk. It's now 2 a.m. in Australia. I might instead be recognizing a high-flying, well-established academic who I have read about for years and formed a somewhat parasocial relationship with. However, just as I'm aware that I have formed these kinds of alternatives, I can reflect on the relative likelihood that I truly do know and do recognize this person. And this metacognitive appraisal of my simulated belief means I can safeguard against the chance that I might be wrong by perhaps frantically waving at them from across the room, but refraining from chasing them down to give them a hug. This kind of uncertainty is often measured using earned tasks like this one here. And this kind of version of it would be very easy to pass. A hand goes in, it picks out a ball, it's going to be a red one, they're all red. Even if you just simulate every possible ball that could come out, you'll always give the correct response. Contrast that with the addition of proportion or probability-based information. And to pass this one, you need to understand that there are mutually exclusive future alternatives. The hand goes in, it picks just one ball, it could be red or it could be blue. There is an extensive body of work on possibilities literature, pointing to the idea that it sort of emerges at a capacity around 3 or 4, or potentially even younger. But reasoning under uncertainty, often studied with these kinds of earned tasks, where you draw samples that are either consistent or inconsistent with the visible population in the urn, and take measurements of uncertainty or violation of expectation, like look time and pupillometry. Using these or choice behaviors between two contrasting urns with two contrasting or competing distributions, the long history of research suggests that even infants are sensitive to probabilities given differences in these kinds of implicit behaviors, while some more recent findings suggest that it might emerge as a capacity much later on. To reconcile, or perhaps more accurately sidestep this kind of discrepancy to make friends rather than enemies on the first day of a conference, I'm going to frame all of these as the experience of uncertainty. That is, that implicit measures could be predicting or predicated on a state-based experience of surprise or uncertainty in whatever form of representation you choose. So you didn't need to compute proportions to see that between these two urns, it's quite difficult to distinguish which color would be more likely or which urn would be more likely to produce a red ball. Given a process like implicit statistical learning or perceptual sensitivity, you should not feel surprised and that kind of uncomfortable feeling of surprise or discomfort if either color ball emerged from either of the two urns. Then not only reflexive behaviors, but even choices like opting out, which is seen in some monkey tasks, don't necessitate appraisal nor calibration to uncertainty. They don't require the capacity to understand possibilities and probabilities. By contrast, if perception and cognition that you have, for example, you might simulate her at the conference and think, isn't that delightful Australian from that wonderful talk session, is also coupled with an explicit awareness of the limitations of your knowledge, that you could be wrong, then you have a meta-representation. Importantly, to understand probabilities, children must simulate multiple possible outcomes simultaneously so that they can reflect on the relative likelihood of each of these alternative simulations, the same basis from which you would compute your confidence. So in that regard, metacognition poses a really important and valuable way to get insights into these kinds of processes. So when that reasoning about uncertainty can be distinguished from reasoning under uncertainty, there should be variation of confidence in your judgment based on the probabilistic evidence. So you should be more confident as you are more likely to be correct or the probability aligns with your choice, and less confident when you are less likely to be correct. There is quite a large existing metacognitive research area that focuses on and suggests that children can calibrate their confidence between accurate and inaccurate choices that they've made using 2 or 3 point scales. In a probabilistic context, however, your prediction should instead be calibrated to the overall likelihood. So looking at confidence not just based on children's internal state of uncertainty or the strength of their memory trace or their performance, but the variable probabilistic information that their judgment is actually correct. So if children truly understand probabilities, they must represent the continuum of likelihoods and calibrate their confidence to that continuum as well. Although probability is fine-grained, here the problem you would run into is that you are unlikely to choose red as the chosen option. There are, in fact, more blue balls, and therefore the accurate choice would be blue, and it's hard to get sort of the low-level confidence that would reflect that sort of unlikely choice. We can get around that in the present task by, instead of using that two-alternative force choice, having decisions with multiple alternatives or urns that contain a multitude of different colors, in our case up to 4. And then you can leverage a more sensitive explicit measure of confidence to see whether children's confidence tracks the relative probability of the chosen option across the full range of probabilistic outcomes, including things that are unlikely, likely, or even guaranteed. So those are the three frameworks I will use in this talk. Firstly, asking how children make predictions in uncertain situations. Secondly, whether or not they have insight into the relative likelihood of their predictions. And finally, whether or not we can distinguish any of this kind of insight to either implicit or explicit forms of uncertainty. We do that using two measures. The first is reaction time. It's very sensitive, it's implicit, and while it might not necessarily be metacognitive in the traditional sense, it's definitely a related construct. It's established and quite easy to implement. We'll also use a novel confidence scale. In our case, it is this cup. We say fill it all the way to the top if you're very sure, leave it all the way empty if you're very unsure. It's very sensitive, it has 120 points of sensitivity in it, and we teach children how to use this and have two manipulation checks. Firstly, we ask them to show us how they will fill it, very high, medium, or low, if their confidence corresponds to that. And secondly, we ask them how sure they are of their own name and of an unknown character's name, which works quite well as long as you remember the child's name. In terms of the actual framework of the task, we first show them the probability distribution. We show them this as a picture on a blacked out jar so that the information inside the jar, sort of random variation in the location of the balls, won't influence the judgments. Then the experimenter, present with these 4 response jars, asks where the ball drawn out of this urn should be placed. The child will then make a response using an iPad, which has pictorial representations of those 4 jars, and that's where we take the response latency measure as well. Then the experimenter asks them how sure they are, and they respond on the cup scale, where they can drag it with their finger, full or empty. They make that judgment, and then the experimenter will draw that ball out and put it into one of those 4 response jars without showing them the color. So we can delineate the kind of probability distribution where there is a best option. In this case, the lowest best option or the least likely one will have 4, because in the case where there are 3 of each of the 4 colors, there's no clear best option or no best option at all. Contrasting that with, and they should be not particularly confident, contrasting that with trials where there is a best option or a sort of clear best prediction where the overwhelming evidence is in support of that best option. We vary the degree of evidence for that best option across these trials. So they should be more confident in that situation. In our task, we tested 64 children aged 3 to 6 and did not give them feedback, as I alluded to, with 13 counterbalanced trials, counterbalancing for the orientation, the order of the trials, the location of response jars, and all of those kinds of good things. We have a couple of different trial types. The first is, as I alluded to, one where there is no correct option. There are 4 guaranteed options with each of the 4 colors, and then there is a gradation with 8 trials in between that at every possible level of probability between a 4 and 11 out of 12 balls. So what did we actually find? Accuracy is kind of an odd construct to talk about in this case, because as I said, we don't give them a sort of result or the outcome of the draw, so it's based only on whether or not they chose that most likely option. The x-axis along these graphs correspond to the proportion out of 12. In this case, going from 4, because 3 has no correct answer, all the way up to 12, a guaranteed trial. Our analysis used GLMMs nested within participants with random intercepts. We found significant main effects of both age and probability, as well as an interaction where we were treating age as linear. So what you're seeing here is the follow-ups, where we have broken that into the 4 age groups. So in this first one here, you can see with 3-year-olds, as compared to that red dotted line, which corresponds to chance, it increases so substantially because it's based on the idea that they are randomly sampling one of those 12 balls. So they should always be accurate at 12, all the way down to 25% accuracy at 4. So they are performing largely quite close to chance, but slightly below it. 4-year-olds are doing the same. whereas 5 and 6-year-olds are performing both above chance. However, in this context, all 4 age groups are sensitive to probabilistic information. But if we actually look at their relationship to chance, we can say that with older children, they're performing significantly above chance at those lower thresholds. At the higher thresholds, it's quite hard to perform above chance because there is not a lot of room for error if a couple of kids are performing or choosing either an impossible answer or that 1 as compared to the 11, then it will drop out of the chance range quite quickly. But contrasting that with the younger children, where we see that they are performing around about chance at those lower trials, the sort of harder ones, and then at the easier trials, they're performing significantly below chance. So this would suggest that to the extent that they are randomly sampling, they're not doing so at least from the whole array. So there is a subset or perhaps heuristics. For example, in that 11 trial, there's only 1 color that is not the majority color, and therefore it has quite a sort of pop-out effect that could be related to the way that younger children in particular are making these choices. So going back to the graph we had from before, which shows the accuracy progression, we can also look at the special case of 12, where that would constitute a guaranteed trial. So that's kind of different from the rest of the continuum because, first of all, it's pulling that quite strongly because there are 4 trials as compared to the others all holding 1. And so it's also quite semantically different because it shows a guaranteed outcome where there's no need or sort of capacity to do sort of simulations. Any simulation that you do outside of that guaranteed outcome would be incorrect. So we can also look at how it tracks when we remove that guaranteed outcome. And we can see that the accuracy drops quite substantially for 3 and 4-year-olds as compared to our 5 and 6-year-olds who are still performing above chance across the board, or mostly across the board. Then turning to our metacognitive calibration, firstly we can look at the replication of existing measures that looked at the distinguishing between accurate and inaccurate trials. And we can see that for reaction time, we do see a statistically significant difference across the full sample, such that children respond more quickly when they are accurate. And in terms of explicit confidence, they report higher confidence when they are accurate as well. That's controlling for the probability of the information in these particular models, but given that's quite collinear with accuracy, I take that with a grain of salt. And so how this actually breaks down into each of the age groups when we follow up the interaction that we also have in our response latency, we see that from 3, 4, 5, and 6-year-olds, we see implicit sort of disentanglement or an effect of probabilistic information. What that kind of means is that overall they are, to some extent, sensitive to this kind of probabilistic information. But as I alluded to before, because of the inclusion of that 12, where there is only a guaranteed option, it's also including not just probabilistic information, but also possibility-based information. So if we remove, in the same case, that sort of guaranteed trial set, by this contrast here, you can see that 3 and 4-year-olds drop out of a significant effect, which kind of points to these guaranteed trials as being the thing driving that kind of difference in how quickly they are responding. In terms of confidence then, we see that 3-year-olds show no effect across the board. The line completely flat. If you look at the data, weirdly U-shaped. 4-year-olds start to show that effect and do show it at a significant level, less than 0.01. 5-year-olds show it, and 6-year-olds show it quite strongly, and this is what my supervisor calls absolutely beautiful data. If we can, just for the hell of it, also remove the guaranteed trials here, you see that there's not a huge kind of difference. The 3, 4s, and 5s all drop out of significance, with those 5s sitting at 0.052 significance level, whereas 6-year-olds still quite compellingly show that result. So controlling for probabilistic information as opposed to possibility-based information, it is 6-year-olds who are really showing the strongest, and in this case, only sort of calibration of metacognition. Now, some of you might be thinking after the first talk that there is a really big possibility that language plays a role in this, and that given that we're looking at explicit metacognition, that the way that we understand concepts like confidence are quite complicated, especially for our 3-year-olds. And so showing you here our first manipulation check, where we asked them to show how they would fill up the cup, if they were very sure, if they were not sure, and if they were somewhere in between, in reverse order, just to keep the drama and suspense alive. 6-year-olds can do it, 5-year-olds can do it as well. 4-year-olds can, and you might have guessed by the fact I'm showing this graph, 3-year-olds can do it as well. So with this kind of prompting at least, we see that all children in our age group can show these differences and can kind of use the scale at least to some extent. So overall, what do we kind of find? Our 3 and 4-year-olds vary in accuracy with guaranteed outcomes, so that inclusion of a 12 out of 12 guarantee, whereas 5 and 6-year-olds use probabilistic information. In terms of reaction time, our 3s and 4s show implicit sensitivity only to possibilities, so when, again, those guarantee trials are included, whereas our 5s and 6s use probabilistic information, and our 4s, 5s, and 6-year-olds show confidence calibration, but only our 6-year-olds robustly show confidence for probabilities. Overall, this suggests that young children might be using some kind of sampling approach to the task, but using either a subset of the information or some form of heuristic. Secondly, that any alternative possibilities might induce at least some extent of implicit uncertainty, sort of streamlining the results that we see from younger children as well, and inducing the need to sort of perform these simulations. But it is only our 6-year-olds that show this awareness across probabilities, and for 4s and 5s, it's only across the space where we bridge the gap between the modal possibilities of something that is certain or not certain. So those are my conclusions across the 3 areas. I would like to thank my fantastic supervisors, John and Dave, the families who participated in our research and my lab, and all of you for listening. I hope that if you see me around, you will wave enthusiastically and confidently.